our next talk, is going to be on balanced POD and ERA. This is a presentation by Mark Luchtenburg and Clancy Rowley, and it will be given by Mark, as he likes to go by, even though it says Dirk up there. So Mark earned his PhD in 2010 from TU Berlin. He since has done a postdoc at Princeton with Clancy Rowley, and is currently a faculty member at the Mechanical Engineering Department at Cooper Union. Mark?
All right, thank you, Doc. So yes, our presentation will be about balanced POD and eigensystem realization algorithm. Both of these methods are data-driven methods that we like to employ for active flow control. So here's an example of that. So this is taken from a paper by Clancy in 2005, so if you want to look that up. So what we do have here is a cavity flow, and we like to control here the oscillations in the shear layer. So in order to do so, there is a actuator here, which is implemented as a body force, and there's a sensor here which senses pressure. Now we could try some method and try to control this flow. But essentially what we want to do really is to come up with like a model that we can actually use to design a flow control. So the original model is of the order of 1 million states. So what we do here is we come up with a reduced order model. Thank you. And we use that reduced order model with 2 states to control the flow. Okay, so here's like this schematically what we really want to achieve with these methods. So we have some flow data, say from an experiment or a simulation. We like to modally decompose them and come up with a reduced order model that we use for model-based feedback control. So the previous talk was more about this picture here, where you actually do a model decomposition to better understand the physics of the flow by looking at the structures of the flow. Okay, so quickly the outline here. So we like to focus on 2 different reduced order model approaches. One uses the Galerkin projection, and we will use proper orthogonal modes and also balanced POD modes to project equations here and illustrate this on an example, which is going to be a channel flow. And then we will also discuss a raw model where we do not use the Galerkin projection, but just data. So that's really just data driven. And I will also show an example of that. Okay, so first let's say some words about Galerkin projection. So again, our goal is here to basically have these high dimensional dynamics. So as we saw in the example, maybe of the order of 1 million. And we like to project them down to a low dimensional subspace so we can come up with a reduced order model for flow control. So imagine that our dynamics are governed here by this differential equation. So x here, the state. And again, this basically this formulation here assumes that you have discretized, say, your Navier-Stokes equations. So say, for instance, we will find a different method that Tim discussed before. So here x represents, say, the velocity. And what we do is we'll project these equations here with a biorthogonal projection. And the key really here is that we restrict our dynamics. So if you look here, the velocity only lives in a low dimensional subspace, which is sort of depicted in this picture here. So imagine like Tim also had a similar picture that the state can evolve in this whole space. And now we restrict ourselves to this plane here, which is the low dimensional subspace. So our velocity can only live, so to speak, in this plane here. And that's our subspace, and now we need to come up with a projection in order to get on this subspace. And that is what this surface depicts here. That's the direction projection. So if you carry out this procedure, so you assume you live on your subspace, which now is denoted here by this v times x, and you project here, then you get a set of reduced order equations that describe the evolution in time of the system. So here there are naturally 2 choices, schematically depicted by these planes. So one choice is the choice for your subspace, V, so that's this horizontal plane, and the other set of modes basically describe the direction of the projection. So these are choices that are up to you as you design a reduced order model, and they turn out to be very important. So in the case of POD, these sets of modes turn out to be the same. They are the POD modes. And then another model that I will discuss, the balanced POD, these W and V are going to be different. So you're going to have two sets of modes. Okay, so here we have this once again. So again, the state here represents, say, a velocity field. Now we're going to assume that the velocity field can be decomposed by spatial modes, denoted here by V, and temporal coefficients, denoted by A here. So your velocity field is assumed to be a linear combination of these vectors V here. Then, assuming this subspace, you put that into your dynamic equations, you project, and again you get this evolution equation for the temporal amplitudes A. So if you think about doing this for Navier-Stokes, then this nonlinear term on the right-hand side basically consists of two parts. A linear part, that's for the diffusion part in the Navier-Stokes, and this Q here, which represents the quadratic part, which is the convection term in the Navier-Stokes. So what you can do now is plug in basically again the assumption for the subspace here and project with W, and you get this set of equations. So this is typically what you see if you do a projection of the Navier-Stokes equations. Okay, so we're going to simplify ourselves a little bit here. So we're going to just be talking about linear equations. So we assume we have access to like a simulator, say CFD simulation or some sort of experiment. We assume that the dynamics are going to be governed by linear equations. And one point that I need to point out here is now time is assumed to be discrete. So instead of continuous time, we have discrete time. We're going from k to k plus 1, which is just one time sample. And the way we're going to get our modes is by prescribing some initial condition, maybe have some actuation input, so it could be a body force in the simulation or some actuator that you have sitting on the body in experiment. And those go into the experiment or the plant, and we can make measurements with sensors, or if we have access to a simulation, right, a CFD simulator, we can get some snapshots out of that. So this is data we can use for model development. Okay, so that's our full order system. And again, I'm going to illustrate quickly this projection procedure. So again, here we have our high-dimensional system. It's linearized now in discrete time. Our state is in a very high dimension, maybe of the order of 1 million. We want to produce a low-order model. So we find ourselves a set of modes, W and V, and we project our equations. And then we get these equations here. And because of the assumption of that we live in a subspace of dimension R, now we have a system that is of the order R, which may be order 100. So say we go from 1 million to 100. Now the question, of course, is which modes are we going to be picking for this projection? Which W and which V are we going to pick here? So first choice here is POD, and it's explained in great detail. I'll take a shortcut here, and for our case, POD simply boils down to a singular value decomposition. So what you do is you take snapshots, so either with a, say, simulator like a CFD simulation, or maybe you get PIV snapshots, you put them into a matrix, you stack them there as vectors, and then you compute an SVD, and then this part here gives you the POD modes. Okay? So these modes basically optimally span your snapshot ensemble in the sense of that they contain the most energy in the data. However, if you do that, then you just have modes that are optimized for fluctuation energy. So this can be a real issue for non-normal systems that Tim also discussed, where you have transient growth. So most of the time, in these kinds of flows, you can have small energy perturbations, which cause a large transient. And then, since POD averages over all snapshots, so it optimizes the energy over all snapshots, you don't necessarily capture important dynamics of the system. Okay, so now in contrast to the POD method, the BPOD method, so the underlying theme here is really, it's a method that we take from control theory. It's a linear method. And direct application of this method is basically impossible for fluid simulations, since you have to solve a large set of equations. You have to solve Lyapunov equations and compute gramians, and that turns out to be a very big problem to solve. So what BPOD does, it basically makes this balanced truncation possible by using so-called empirical gramians. So instead of solving for big matrices, now we're going to be using empirical gramians, which are composed of snapshots. Okay. So that's what I have here on the slide. So I just give you one example to give you a feeling for this. So you can define something like controllability gramian, which basically describes how controllable your system is, or how controllable certain states are in your system. And like I said, you can compute it as a solution of a big equation, or you can take this approach as we do in BPOD. We know the definition of this gramian, and then we basically are going to approximate it with a finite number of terms. So instead of taking this summation here to infinity, we're going to take it to a finite number. Okay. Like I said, POD balances the controllability in the system and the observability. So now we're not just looking at energy, but we see like how well can we observe something, and how well can we control it. So in terms of modes, we say that the most controllable states are most. Those are the modes that you easily excite with your body force. So that's going to be important for us since we're interested in dynamics. Also, if we have sensors, right, then we're also interested in the states that you can see really well with that particular sensor. So that gives you a sense of observability. So we want to balance these two concepts and get modes that now describes the dynamics that we're interested in. So in order now to approximate these gramians, what you have to do is you have to run a simulation. And what you do is you compute first the impulse response of the primal system. So for our first equation, so this basically is just impulse response. You pick your you take your actuator, right? You give it an impulsive response, and then you look at the signal till it dies out, and you gather all that data in what we call a data matrix. And now you do the same thing, but now for the adjoint system. So you basically work now with A transposed or H Hermitian, as Tim showed. And if you compute these two impulse responses and you multiply them together, you do an SVD again, you can compute POD modes, BPOD modes, which are balanced. So there's one thing here, right? Since we do need access to the joint system, you can only really do this in a simulation environment. Okay, so that's a little bit of the background. Now let's go to an example. So here we have a channel flow, and we linearize it around a parallel shear, about a parallel shear flow. So that's around this thing here. And we assume streamlines, constant perturbations, and we solve this using spectral collocation. So Chebyshev in this direction, and then in the z direction we use a Fourier assumption. And like I said, the dynamics are going to be linearized, so they're going to evolve according to this equation here. And somewhere in this domain here, we're going to have a perturbation, a body force that will provide the input to our problem here. And we assume we observe all states. Okay? So here is something that is typical of non-normal flow. So here we plot the norm of the solution, which you can interpret as a kind of energy, and we follow it in time. We see that first this norm rises and then it drops, so you get large transient growth. And using this data ensemble, so for say 60 time units, we compute POD modes. So here I plot these POD modes. So these are the modes we're going to be using for projection, and since the states contain velocity and vorticity, I plot both here, but they're just part of the same mode. So these are just two modes, and we're going to use these two modes for projection and form a reduced order model. So here's the result of that. So we really take it to the max by just looking at basically two states here. So we went from 480 to 2 now. And we look again at the impulse response. So we first simulate the full system, we do the impulse response, so that's the same picture as before. That's the black line. Now we reduce our model with a POD projection, and then we see the blue line. and you really see like this model doesn't do a good job. However, if you look at balanced truncation, and BPOD is an approximation of that, you see that even a two-order model captures this transient really well. Okay, so that's the impulse response. Now let's look here at the infinity norm of the relative error. So then theoretically you can show that this black line here is the minimum that you can possibly achieve, and the blue line here depicts what you get for increasing model order with a POD-based model. So our simulation is for this case here that the model order equals 2. Now if you keep increasing the model order, so here finally we arrive at a model order of 10, meaning 10 states, then of course we get a smaller error and we get closer to our full system. Okay, so we used all the data for this particular example, meaning like we waited till this transient died out completely. The question is, can we get away with less data? So the answer, fortunately, is most of the time we can, yes. So if you look here at this matrix, which again contains the snapshots of the impulse response, then at some point the rank of this matrix is going to saturate. In other words, as you keep going, new snapshots don't bring any new information. So that's often the case. So if we somehow watch the rank of this matrix and it saturates, then we know that we have enough data to model the system, and we don't need to simulate till the transient has died out. So this idea I show in this picture on the right, on the left here, where you basically versus time have the numerical rank. So that's based on the gramian of that impulse response matrix, and you track that in time, the rank, and you see that at some point it levels off. And you could plot it for a longer time, but it basically settles around the value of 13. So supposedly that's the order that we're dealing with here. So, and again here I plot this plot where you see the POD reduced order model and its relative error. So the question is now, can we get closer to this lower bound? Right? Can we somehow do that? And the answer is yes, we can. What we're going to do now is we're going to basically take snapshots up to this particular point in time. So it seems like these are not enough snapshots, right? Because the rank has it saturated. So that means if I take more and more snapshots, new information is still coming in based on the rank. But I just ignore that and say I'm just going to take snapshots up to that point. And now I'm going to build a controllable realization. So I'm going to make a reduced order POD model based on 10 modes. Okay, and that model I'm going to use balanced truncation on. So if you now look at this yellow line here, you see again a relative error, right, versus the model order. So what you do see here, if you first compute a 10 order model, right, and you balance it, so meaning you apply now balanced truncation, you can actually really reduce the error and bring it close to balanced truncation for the full system. Now, since this is a 10-mode controllable realization, of course, the controllable realization, if you reduce the rank of that, it finally is going to have the same order, the same error, but it takes a while. You need a model order for 10, whereas if you first take the full controllable realization and then balance, at order 3 already get a good model. Okay, and of course one can continue this procedure, taking account more and more snapshots, and then you will see that you quicker and quicker converge to the best you can do with balanced truncation. So the story here really is what you want to do is get the maximum rank model and then balance based upon that model. Now the cool thing is you can use a similar approach for the standard BPOD procedure. So you can build up your impulse responses. So this is of the primal system, right? And then you do this also of the adjoint system. So this is the impulse response of the adjoint system. And if you look at the rank of these two matrices, then you can basically say, okay, my rank is saturated, I have enough snapshots, I can stop and compute a reduced order model. So that's what we do here. So basically, again, we take snapshots up to t equals 10, which we know from before, that's actually not enough data because there's still new information coming in. However, we decide to build a model based on this amount of data. And now what we do is we use the snapshots that we have to build a BPOD model. And we balance this BPOD model with balanced truncation. And that's why I call this modified BPOD. And you see that you get a really quick convergence of the error here. Okay. So finally, I like to talk about a model procedure. So these two model procedures with the POD and the BPOD were all based on Galerkin projection. Now there's an equivalent method to BPOD, which does not require joint simulations, right? And you can just work with the impulse response seen with a sensor. So this means you can actually apply this method to an experiment. But the outcome is a reduced order model that is completely equivalent to the reduced order model that you get with the balanced BPOD procedure. So like I said, you don't need full state impulse responses. You don't need to know about the dynamics. You can also tackle unstable systems, and modes are not explicitly computed. So there's no projection here. And it works for both experimental and simulated data. A point that I like to stipulate, and that I showed you already in the previous slide, what you really want to do is keep a full model order and then balance it. So that really means that all these model reduction methods should first have the full set of modes, or as much as possible, and then you want to balance. Okay, so here's practically how you would work with the ERA method. So here you see again a snapshot matrix. This is basically an impulse response of the linear system. So just read this as like a sensor signal, right? And then what you do with these with this signal, you stack it into a matrix, an Hankel matrix, and you shift that whole sequence by one time step, and then you put that in another Hankel matrix, and then you compute a singular value decomposition of the first Hankel matrix. And using that singular value decomposition, you can now compute a reduced order model. And you see this other Hankel matrix showing up here. And it turns out, if you work this out, that this is completely equivalent to the projected matrices that you get out of the procedure with balanced BPOD. So this is really great news. So now we have something that can work in an experiment. So the last example that I have here is a 2D cylinder wake. So this is CFD data, Reynolds number of 100, linearized Navier-Stokes equation. So our actuation input is this body force here behind the cylinder, and we measure the flow at 3 places. And we use an impulsive input. So we do an impulsive input for this body force here, right? And then we watch what happens at these 3 sensors. So that's the impulse response of our system. Now we stick that into a Hankel matrix, and then we can do the model, reduced order model procedure. Just to give you an idea of what this flow looks like if you're excited with an impulsive response, here's the first sensor signal. So if you go back here, I think that's the one over there. Then you get this signal here, evolves like this in time. And if you compute the numerical rank of this data set, then it saturates at around this time here. So that's about 180. Meaning you should have enough data if you gather snapshots up to this point in time. Okay, and that's what you see in this plot here. So you see that the numerical rank of your Hankel matrix converges. And then here we actually do a reduced order model. So let me be clear on this one. So first what we're doing is we compute a realization with ERA, okay? And we use this realization that we get with ERA to compute a balanced model. So in other words, we get a reduced order model for ERA. We use balanced truncation on that. And then we plot the model error here. So if you look now at the red crosses here, that's the error that you get. And you see that this error converges right away for a 6-order model. Now, if you just do plain ERA, okay, so you don't do any post-processing on the ERA, no post-processing, and you just keep 6 modes of your data, then as you go forth in time, you see that it takes really long to get this error. Whereas if you balance the thing with BPOD or balanced truncation, right, then you achieve this small error almost right away. So the message here is really keep as high of an order with ERA as you can, and then balance that model that you have. Okay, so here are my conclusions. So BOD with Galerkin projection is a very good generic tool, right? Because it doesn't require linear assumption, so you can apply it to any data set. However, as we've shown for non-normal flows, this doesn't really work too well. So in the case where you have, for instance, have large transient growth, you really want to use a balancing POD method. However, that requires that you have access to the impulse responses. And in general, I want to stipulate here, and that's basically the point that I try to make during this presentation, that really what you want to do with BPOD and ERA is to keep, to use them for model reduction, but then keep the maximum rank, right, and then balance after the fact, so you get the best model that you can. All right, so that was my presentations. Are there any questions? Thank you.
We have time for a question or two for Mark, if there are any from the audience.
All right.
Okay. Well, thank you. We're gonna move on. So thanks very much, Mark.